Hello, Javed. Hello. Hello, Javed. Vaibhav, can you hear me? Yogesh. Hi, Divakar. How are you? Can you hear me? Hi, how are you?
Your voice is too low.
Can you hear me? So,
Yeah, now it is better. Yeah, now I can.
okay.
Right now. Yeah.
So, Divakar, when did you arrive there?
Yesterday I arrived here.
So is everything is fine?
Everything is fine. Yeah.
Okay.
Very nicely here.
I'm sorry I am not here there. Actually, I was not knowing about your plan earlier.
Yeah. When I wrote to you, it's already late. You were already there.
Yeah. It's just I was already there.
Yeah.
So how long you're planning to stay in India?
Yeah, actually, it's my last few days. Yeah, basically tomorrow he is leaving for day. Yeah, and Monday I'm going day after tomorrow. Yeah.
Okay.
Yeah, from here, but from India also from Monday I'm leaving.
Oh, on Monday you are leaving, right?
Yeah.
I see.
I've been here the amount of time, but I'm going there.
Okay.
Auditorium, how do I connect? Let me connect and talk, okay? You can present to a different view. Plus minus 50 just so that one side actually आएगा सर नहीं आ जाएगा तो अच्छा अभी सांस बोलो नहीं वैसे नहीं बोल रहा है आज ही आपने एक नई बीमारी चले है एक आ जाएगा प्लान में है नंबर है मोबाइल में नहीं एक्चुअली हुआ ये था इन्होंने बिल जमा नहीं किया एडमिन से वो किया नहीं डालने तो आउटसाइड वो क्या कैंटीन से आनी चाहिए किसी कैंटीन तो कनेक्ट कर पाते हैं 850 नहीं आप फोन से नहीं कनेक्ट किया नहीं डाउन फोन से तो नहीं डाउन 100 तो मुझे बाहर आया अभी शेयर स्क्रीन लगा हां okay, just right. Yes, right. If you want it.
This is the way, right?
Yeah, this is
Necessary to practice.
yeah.
There is another possible.
This one is wrong.
That is from whom?
नहीं वो सिस्टम से हाँ
There is one. This mouse is yours.
इसमें डीले है इसमें थोड़ा सा लग रहा है डीले है हाँ वो वाईफाई से है ना
Yeah, no, this is not there.
हो जा रहा है
No, this is not. Oh, again connecting.
अरे इंटरनेट का प्रॉब्लम है
Internet problem. Yes. That is the rest.
वो फॉरवर्ड नहीं लेकिन हमने ऑनलाइन तो कुछ करना है कौन सा एक्सेस फॉर्म में कनेक्ट किया वो देखिए
No, LAN को दूसरे connection.
अभी
I'm still no. I'm out of the share.
yeah so we
तो यहाँ देना पड़ेगा
हाँ उधर लाइन आप उधर आ जाए के साथ फिर और भी
ठीक है हमने ऑनलाइन की सकते
हाँ ऑनलाइन तो लाइन पे
अभी वो कर रहे हैं एंड्रॉइड में लेके वही वही कर रहे हैं हम ये अनस्टेबल रहेगा
मैं पैरेलली सब चार्ज करता हूँ वाईफाई का रिमोट यूज
Wi-Fi.
वो कनेक्ट हो रहा है बराबर तीन बार हुआ है
Yeah.
मैं चार्ज मैं पैरेलली
Yeah, it is ready. Let me.
switch it
Yeah.
that's one
Yeah. Now my computer is.
टिंगो में डाटा ड्रॉप आ रहा है टिंगो में डाटा ड्रॉप ये सही है पर आज भी वो मैनेज करता है क्योंकि उतना ये नहीं हो रहा है now change over right yes
no issue
Anyway. Yeah. Okay. Takes some time.
no now you can
Okay. Sure. Very nice.
okay so hello
Wait this way. It's on here now. When is on?
so the PDF file
Yes. It's PDF. Huh?
So good afternoon, everyone. So thanks for coming today. So welcome to today's colloquium. And today we have a speaker, Divakara Mayya, and I would like to invite Professor Divakara Banerjee to introduce the speaker and yeah, process.
Good afternoon. It's a pleasure for me to introduce to you today's speaker, Divakara. We have long connection. So when we joined as a student in IA, Divakara was the only senior student at IA. So he's a JAP student. He is a JAP student, I should say, because JAP is a sort of lifetime affiliation. So he joined English of Science as a JAP student, 86. And 87, he moved to IA. Those days, of course, part of the joint assessment program, many institutes were there, but IA was not getting many students regularly. So I decided to take some more students from the JAP interview or otherwise from 1990. So 1990, when we joined, Divakara was the only student. Senior to us, but he was even as he looks today also like a student. Those days it was difficult to convince ourselves that he is our senior student. Divakara was always very friendly, and he was our only help for solving assignment problems. Because now you have more senior students, he was the only guy, but as usually he will not solve anything. You will ask more questions. Why this, why that? But we had really fun time. We used to meet late in the evenings, almost up to midnight. And so we learned a lot of stuff actually. We used to go with our assignment problems to him, and he will ensure that we understood the subject before giving the tips to solve the assignment. Even I remember our first presentations were all so during the coursework also we had projects, and then we have to make some slides, but those days it was transparency. I think last few years of handwritten transparencies. We have the overhead projectors that so we didn't know how to write transparent. This is also again Divakara was our only help. So having said that, so Divakara finished his PhD from IIA. But interestingly, this was also a learning lesson for a lot of us. He was the first user of the CCD camera which came. You can imagine 1990, first generation CCDs. He was just even mentioning yesterday, no software. The camera is there, but how to read files from the thing was also written by them. And we were actually all worried because Divakara was known to be a very good student. But almost 5 years, he didn't have a publication because he was still starting to read the files. So how to publish? But because of his generation, people, things got settled and so on. But since he learned things from first principle, you think about he never had any problem of getting subsequent jobs and all that. So he finished his PhD, went to TIFR as a postdoc. 2 years in TIFR and moved to Mexico. And since then he's still in Mexico. So he's permanent staff there for many, many years. And he's built that group also, I understand. And more recently, we are able to connect him back. And he says that ASI has to be thanked because we started, looking our alumni and started giving them emails and so on. So I'm really thankful, Divakara, for coming here all the way. So he has already made few visits to other institutes, and tomorrow Brijesh will take Divakara. So you'll see what changed in 1990. 2.6, 2.4 meter, 0.34 meter. It's nice. Vainu telescope, and now the modern technology. So without further delay, let me invite Divakara.
So thank you, Divakara, for all the nostalgic introduction, and thank you for being here. So I'm happy to be here. I've been hearing about Nainital from 80s, because I was very friendly with Ramsagar, and he had a lot of connection here. But it's the first time I'm coming here now after so many years. So I'm really thankful for Divakara for arranging all this possible. No? So I had this plan. I am on vacation now, but I said, okay, Divakara, that I want to come here and see whatever here. No? So thanks. So today's I've been working all these years on nearby galaxies. That was my thesis actually, is forming regions in nearby galaxies, one of those kind of objects. So I've been continuing in the same subject, but in these decades, technology has changed, and the definition of nearby itself has changed, and how much we can see in my thesis base. One blog here is measuring kiloparsecs, but these days, thanks to HST and now the James Webb images, now I can talk about parsecs. So that's the difference. So here in this particular work, I am presenting basically the creation of in general bubbles, but in particular what is the theory behind the creation of this large bubble. So this image is of galaxy NGC628. NGC628, one of the late type galaxies, with the star formation rate of around 2 solar mass per year. And in these kind of galaxies, after when the James Webb telescope started taking images, so it showed several of these this whole kind of structures. So people started calling these galaxies like phantom galaxies. So look at the textbook, you won't have definition of phantom galaxy. It's completely social red driven nomenclature. So, but this is the first of such category. So, and this appearance comes because there are so many holes, which I will call in this talk as bubbles. So that's the definition. I will answer what is the theory behind the creation of these kind of bubbles. So this work is James Webb based. So James Webb, as you might know, it was launched on Christmas Day in 21, so which is just a year ago. And in July, on July 12th, first data were released, and this galaxy was not included as the first release. It came in sometime in July. So the data was taken for some other program, and it became public. So I started looking at that big bubble and trying to really answer the question of what created those bubbles. So in a few months, we could understand the complete and understand that bubble and write a paper. And while I'm on vacation, it's almost accepted. So some small changes in the figure, Priyas, nothing else. So this work is done basically by my group members, as Divakara mentioned. So group members keep coming and going, like students go and they become postdocs, go somewhere else. So the first, after me, first author is Jairo Alzate, he's a postdoc with me. So, and next one, Luis Lomeli was a student with me, he's postdoc in Brazil now. So others are, most of them are colleagues at my institute, which is called as INAOE in Puebla, Mexico. So this image that I showed was taken with the JWST, but in the mid-infrared filters. The name of the instrument is called MIRI. So that takes images between 5 to 30 microns. It has several filters. So this for this galaxy, it has been observed in 4 filters. So I can, according to me, first button now.
Yes, sir.
Okay, good. I can show you. So the in these 4 filters that are centered at 7.7 micron, 10 micron, 11.3 micron, and 21 micron. So at the 21 micron, the resolution is 0.6 arcseconds. So this is really, really good. Whereas in this image, it's around 0.25 arcseconds. So that's the kind of resolution. So this galaxy is at a distance of 10 megaparsec. So we get 1/4 of 50, around 10, 12 parsec kind of resolution in this galaxy. So this bubble measures around 1 kiloparsec. So it's too big to be normally explained as due to due to, well, the bubbles are normally explained as due to feedback effects of massive stars. So either stellar winds or supernova explosions, or combined effect of both these kind of effects. So usual bubbles created from these processes are around 100 parsecs. This is 1 kiloparsec. So we need to understand what is the theory behind that. So before I go into the detail, just searching at why this bubble is seen more in these two filters, especially at 7.7 micron. So 7.7 micron filter intercepts the polycyclic aromatic hydrocarbon features at around 7 micron there. So these pH features can get excited by some shocks or by radiation that is not very energetic. If O star is there very close by, it will destroy these pH molecules, but the milder stars can excite and illuminate these regions. So we are seeing the edge of what is a cavity there, which is basically black in this figure. So, well, I already explained what can be a possible method to create these bubbles, but that is consecutive supernova explosions. But there can be there are in literature other processes like a gamma ray burst site can have also a very big bubble. Or another process that was invoked is by who is a colleague now at INAOE, is my next door colleague, who has proposed, for example, impact of high velocity cloud, and high velocity cloud can impinge on the galactic disk and displace the material. So that also looks like a hole in the H1 images. So, but the characteristic signature of the first process, the first process is the presence of remnant stellar cluster. So if the bubble is created due to feedback from massive stars are dying or already died. So, but there will be not so massive stars which are clustered normally. So then there should be a cluster sitting inside. No, that's the one actually here we are after. No, so we used many observations to search for these stellar clusters. So not only the stellar cluster, also we studied, used multi-band data to study the morphology of the bubble itself. So that way we could characterize the multiphase morphology of the interstellar medium surrounding the bubble. So the data we used are all public. In this whole data that I am presenting here, all public. And but they are the best data available at these bands. So it is the quality of public database these days we have. So this, for example, we used the neutral hydrogen, 12 lakh second resolution. So CO from ALMA, and alpha data, VLT, MUSE, and the 7.7 micron using the James Webb telescope. So obviously that is the best resolution image, and with availability of CO image helps. CO is the data cube, so helps us to study the kinematics of the shell also, whether it's expanding or not. And we use the HST images along with the James Webb NIRCam, that is near infrared band images, to trace or to look for the possible stellar cluster. And I already showed you 21 micron images. 21 micron is infrared, infrared images. They trace any embedded star cluster in any of these in the observed region. So these are all the data set we have used to study this region. So here is a map of these all interstellar medium tracers. So on to the left, you see the 7.7 micron map from the James Webb, where I'm showing the contours at two levels. One, the yellow contours basically enclose what is a cavity, and the blue contours enclose the shell basically. So the same contours here I am superposing on the H alpha image here, CO and H1 image. The resolution of the image in these two is not that good. So CO is decent, but H1 resolution is quite bad compared to what all the resolutions we have them. So you can see already that the bubble is traced in other bands also. But if you see the whole galaxy image in these filters, the bubble is not that visible, that easily visible like in the James Webb image. So because there's so many other structures, the coherent structure is not seen that easily in other filters. But with the James Webb filter, we can easily see, and then if you look for it is there in other bands also. So we find that doing this analysis, the radius of the bubble is around 450 parsec, and the interstellar medium around this cavity is basically molecular. Most of the mass is in this gas, which is around 20 million solar masses. So there's a huge amount of gas is there sitting around this bubble. So you can interrupt me if you have questions. So I'll go on.
So this is sorry. Okay, the previous image.
No, I went opposite direction. Sorry.
Hello. Yes. So this the mass that you have computed here is the mass enclosed in the view computer.
Yeah.
So now you said it is very messy. Is it because of the shock, the plasma got compressed and the density become high outside that? Is that the reason, or there is something else?
Yeah, we are going little ahead of the talk, but this is the swept up mass. It is the
swept up mass because of the shock that is happening.
Yeah.
Okay.
So this criteria, this criteria classify or identify bubbles.
Yeah.
So it's only these images or some other difficult technique?
Yeah, that's a tricky question, but basically you
see other features also can be considered.
yeah, there are now I mean these data are new. So also in December, other papers appeared using the same data. There's a catalog of more than 100 bubble-like structures. But like in astronomy, mostly first work is done morphologically, calling it bubble. Then you need more kinematical studies to establish that this is really a single entity. You know, there is some expansion in such features. Okay.
Yeah, the point is probably there is another dark region on the top left corner.
Yeah.
So why do you ignore that?
Yeah, definitely.
Of course, both the contours, whether it was.
Yeah, sure. This is also a bubble. This also is bubble.
Yeah.
But providing distress. So it is like our interest was to explain this big bubble. Okay. So we are not telling that this is the only bubble there. So there are so many bubbles. Actually, as I will illustrate later on, in H alpha there is another one bubble sitting inside the big bubble itself. So it is like nested bubbles actually. So if there is a big bubble, so it sweeps everything along with it and makes it big.
And why in H alpha you are saying bubble? In H alpha is like high energy, like finite.
Yeah.
So why is there in H alpha? It should be like just cold and thin.
Yeah. Well, H alpha has actually two kinds of emission there. One is diffuse emission, and the other one is a compact emission. Compact in I think in the very next one I have named them. So I'll go to the next one. So the H alpha emission is basically coming from 5 compact regions, which I have named as A, B, C, D, E. No? So more or less. So most of the observed H alpha emission comes from these 5 regions, but there is also some diffuse component which can be seen here. By the way, this is a color combined image, RGB image in 3 filters. So here blue is the H alpha image, and red is the CO image, and did I say in green is the 7.7 micron image where we trace the bubble. So they coincide as we already illustrated, but here you can see that inside the bubble there is some diffuse H alpha, and in this region, because of the contrast here, you can clearly see there is a lot of diffuse H alpha also. So what is, well, the origin of this compact H-alpha emission is because of there are cluster or stars sitting there, so that is the ionization. So the nature of the diffuse emission we have not addressed in this end. So that's an interesting topic by itself. Okay. They are the bright regions in the 7.7 micron image, so 770W what you call that. So that is basically tracing the pH a strong region. So that's the shell, just in the colloquial term. So that is the shell around the cavity. Here I have not plotted H1, so I have CO there. So H1, because the poor resolution of H1 compared to the other, so you cannot see the structures. It's the only resolution is like you can see here. It's not that good. So whereas the CO emission is there's a lot of CO emission on this side, which is like little outside the H-alpha and the pH bright region. So actually, this region also this is the spiral arm actually. So it's grazing actually. So as I'll conclude, the bubble is expanding and it has reached its limit here. So it is already getting shocked with the spiral arm on this side. Okay, I'll move on. So this is the radial intensity profiles in this 4 interstellar medium tracers and the 21 micron image. So here what you have is the 0 is the bubble center, so and the radius in kiloparsecs, and what I'm plotting here is the intensity profiles normalized to 1 at the peak values here. So these are not cuts; these are azimuthally averaged intensity profiles. We needed to subtract in the background. It's difficult to define where is the background for this kind of galaxy, plots. So what I want to conclude from this, there's some details here, is that at the 7.7 micron image, pH is there everywhere in the galaxy. So only wherever there is some bubble, some star formation, the pH is destroyed. So then it's really a cavity. There's no gas, there's no ISM there. So that's what happening here. So it is negative because it's below the general column density of pH in these regions. So H1 also shows a similar characteristics. In general, outside it is here we did subtract here in the H1 the contribution outside. It's quite somewhat difficult to estimate because of poor resolution. So here also in H1 inside the bubble, so you have much lesser density compared to what is outside. So that's why in H1 people call H1 hole. It's basically hole. That's very the contrast between this and this also not that much. So in the other filters there's a lot of contrast. There's really a shell around the cavity, whereas H1 there is no shell. There's a hole, and then there is continuous distribution of H1 like any other part of the galaxy. So this is just illustrating that there is no material inside this cavity. Basically, only whatever is traceable is only in H-alpha, some diffuse emission. Similar plot, but azimuthal intensity profiles. So where A, B, C, D, these points are the H2 regions that I already discussed. So here only for the convention, the position angle is normally defined as positive in anti-clockwise direction. So that's how A, B, C, and D, E. So and then you have so wherever H-alpha bright regions are there, you can see that there is also bright 21 micron region. So 21 micron region is supposed to trace the embedded star forming region. So here, and there is no extra 21 micron source that is not seen in H-alpha. So which also suggests that there are not very heavily embedded sources. So whatever 21 micron sources are there, they have extinction, it may be 1 or 2 magnitudes of magnitude, not 20 magnitudes.
So this is at what radial distance?
If it is it is radial distance, all covering this between 0.4 to almost 1 kilo, 0.7 kilo per second. Yeah, average over that. Yeah. So circular, here we made the circular assumption, which is not exactly some electricity in that. So just for illustrating the distributions. So let me go on to the next topic of whether the shell is expanding. So we use the CO kinematical data here and plotted it against the position angle. So for an expanding bubble, which is participating in galactic rotation, so the azimuthal component of the velocity can be written with this equation, where the systemic velocity, that is the galaxy velocity, and if it's expanding, so this expanding term, so this is the rotation term, where I is the inclination angle of the galaxy. So this is almost based on its inclination about 20 degrees. So theta is the azimuthal angle in the plane of the galaxy, which is related to this position angle here. So, this, if there is no expansion, then the expected relation is whatever is in the dash. Move somewhere else? Yes. My point. Yeah. So this is the dashed lines, but the data fit better with the expansion velocity of 12 kilometers per second. Data which is in this azimuthal range. So we found very interesting there is an azimuthal range where velocity is almost planar, here constant. So and then this simple model doesn't fit that. So we don't know exactly what is the reason for that. So that will be a theme for future investigation. So this region happens to be the zone where the bubble is colliding with the spiral arm, and density of CO is very high. So, but their velocity seems to be constant.
So how the inclination was constant? You said 20
degree inclination of the disk of the galaxy along the line of sight.
Okay, and it was obtained from any
From other previous observations, NED, for example, net used them like 21 degrees. That was obtained using H1 observations and doing the rotation curve of the galaxy and all. That's the way they obtained. Okay, so then from here we conclude that it is a physical shell, it is expanding, so not just a projection effect. No, so it is the gas is dense at the edges and it is expanding at around 12 kilometers per second. So our main interest was to look for the stellar content, you know, if it is formed from feedback effects of massive stars. So then we used all the stellar tracers, that is the HST and James Webb, the near infrared images. So here I am showing them in the increasing order of wavelength. So this is the B filter. So whereas here is the this is a K filter, equivalent to K filter. So this is 3.6 micron filters. No? So in the first image, you can see that there are a lot of stars, and they are bound by these contours, same contours I showed earlier. So selling this, yes, there are stars. That's what we are looking for. So just after doing the astrometry, immediately we got the answer that there are stars which are bound inside. So and whereas that is not that apparent in the James Webb images, which have better resolution than the HST images, these three images, these four images. So that's because at the James Webb resolution, the disk of the galaxy is completely resolved. So there's no smooth disk like here. You see, it's all resolved and there's no extinction effect. So you see the whole disk as a collection of stars, and then these new stars, whatever are born inside, are completely swamped by the underlying the disk stars. So that's why doing astrometry. So all these stars that we see here are available in these images also, but the contrast is lost because of this resolve. I mean, the disk stars are resolved in these images. So what we did was to,
So what's the typical density contrast? I mean, outside the disk, and if you take away from the disk and at least
it depends on the filter. So here, well, number of stars, it's almost double the number of stars, extra stars in the inside the bubble here.
In the optical value, there will be extinction, right?
Yeah.
So you have to normalize with the extinction, then only you can derive like completeness based on the extinction.
Yeah, that is also one aspect. Extinction will that answering the question not that straightforward, but extinction matters. So that is that's an interesting thing here. As I illustrated in the radial intensity profiles, so inside the bubble, the cavity is ISM free. There's no gas there. So
Yeah, that's why I'm asking you optical.
Yeah.
Extinction is more in the like outer.
outside region, exactly.
You are getting more number of stars in the optical.
Yeah,
So
where in the
outer, like in the.
Yeah.
In the,
yeah. That,
not in the.
I get to your point. Let me just clarify. So we get more number of disk stars also here, not just the bubble stars. So I will soon explain how we tackle these problems. Okay. So so what we did was to do the photometry of all the stars here. So using extractor, identifying stars and doing the photometry, and selecting selecting let me continue on that topic before I'll describe this image. So this just illustrates the color image, whatever I had shown before in color. So where you can clearly see that the blue stars are those seen in the HST images, and red are that are shown that are seen in the JWST K-band image. So clearly the blue stars are all contained within the this. So clearly illustrates that there is some excess number of stars inside the bubble. That's the at least qualitatively are sure that there are excess number of stars. How much it is? So we need to do it quantitatively. So
this conclusion that they're young stars is just from other criteria, or
we derive the ages as well. I will describe soon. So so this one of the questions comes from here itself, is that yes, there are a lot of stars, and our initial assumption that there may be we are looking at cluster actually. So we are looking cluster of sizes. Typically here there are many people working on open clusters, so a few parsecs size or tens of parsecs, but we are seeing distribution of stars over kiloparsecs. So it cannot be a cluster which occupies such a large radius. So then maybe it's a destroyed cluster and all the stars got scattered over that much large area. So that's one of the hypotheses. And also we are seeing, we showed that the bubble is expanding, and the H2 regions, as I already remarked, they are at the edge of this bubble. So we are also seeing here some evidence for triggered star formation. So in the talk, I'll answer this, answer positively to this question. So yeah, these are actually we are seeing here the triggered star formation. So this is just to illustrate, although the yeah. So this is the image, same image where the green is the 7.7 micron image, and next is the H alpha is green here. So only difference is, so you can see that in general it looks similar. So but then there are differences, especially if you look at this zone. So a lot of differences. No H alpha here. So but there is a lot of this pH emission. So there's like PDR regions in a river.
clearly the H alpha is more clumpy.
Exactly.
Instability.
H alpha comes from basically H2 regions, whereas this comes from pH from any region in the interstellar medium.
So whenever there is this clumping, there is some, for example, Parker instability also causes this, and since you were linking it with the spiral arms and all that. Is there some linkages there?
To why it is clumpy? That is how the stars form, right? The molecular clouds
Yeah,
break up
Yeah,
and.
but the age and all those also has some relation with that, right? So with phase of these things, you see the clumpiness and then it gets
Okay.
more distributed and all that.
Yeah,
That-
maybe next time it is, since so many things are everywhere, what you're discussing is
Because
very
to form the
difficult.
clumps also, there is a time scale required,
Yeah,
which is related with the galactic, evolution time scale and so on.
yeah. So here the star formation is over a few million years of time scales generally. So, yeah. Exactly, that's what I will show you in one of these plots where I superpose on the H alpha, where you get the answers. No? So what we did now to obtain the ages of these stars, so we obtained also stellar catalogs in some representative disk regions. So it's not that trivial to define which is that region, the representative region. So we just begin with define these 4 regions. So, and found that the BG3, what we call, that is completely different. This is stellar population. So finally, we use these 3, which have more or less similar number of stars as well as the color distribution of the stars. So, and then compared it with the color magnitude diagrams obtained for each of these regions. No? So which I am displaying here. So here what you see is the color magnitude diagram of the stars inside the bubble. So each dot is a star here, and the lines are the isochrons for ages between 3 and 50 million years. 3 is the top here and 50 at the bottom here. So, and these isochrons are from parsec models. It is a Padova group, and for the solar metallicity basically. So this shows that there are stars younger than 50 million years, but comparing it with the disk, so we'll get that answer, how much excess is there. So next one, so this is the disk region. So just you can go back and forth. So you can see that clearly there is an excess in this part of the diagram. So, here we can analyze even for stars fainter than this. So we analyze only up to 24 magnitudes, because below 24 magnitude, we could see that the disk population contamination is serious, and we need to do a lot of extra work. So since our primary interest is to establish that it is a young cluster, or to obtain the ages of this cluster, so we restricted ourselves to 24 magnitude and above. So then the method we have adopted here is to associate an isochron to each star is based on a Bayesian code. So what it does is, for each star, it obtains the probability that it can belong to any one of these isochrons. So from each star, we have not one age, we have a series of ages with some weights. So from that, we can obtain multiplying the probabilities for all the stars, which is the best age for this. So not one age. Actually, these codes directly give the star formation histories for the region. And one of the advantages of this method is that we needn't subtract the disk population. So we'll obtain the age for the disk population also. So then by comparing the star formation histories of the disk population and the bubble, which contains the disk also, so we can obtain the excess ages of the excess stars that are inside the bubble. So that's what I'm illustrating here. The red plot, red histogram, is the star formation history of the average over these background regions, which I call 1, 2, and 4. So average region. So in terms of normalization also, it agrees. So that is the question that you asked, Divakara. So it has more or less same number of stars here, and whereas inside the bubble, there is clearly a population younger than around 50 million years. So more than 50 million years now, we will be entering the serious problems of completeness. So which can be addressed using the James Webb and NIRCam data, which requires some more experience to use it, that are new. So, but with HST, we can now conclude that there is this population younger than 50 million years. So we subtracted these two histograms to obtain this age of the excess population. So the first generation of stars seems to be the most intense, and around it's around 50 million years. So it's in the log age in years. So 7.7 is 50 million years. So after that, there is a smooth decrease. So there are ups and downs in this histogram, which is expected because here I am showing log graph. So delta t is not the same, no? Delta t is fixed in log, but in linear they are different. So number of stars in each is different. So it looks like basically star formation started around 50 million years ago, and after that is slowly decreasing, but it's continuing up to around 4 million years ago. In the last 4 million years, there are no young stars inside the bubble. There are stars older than 4, but most of the stars are older than 10 million years. That's the age of this population. So one of the results that obviously from this figure, that is not peaked at a single age. So that is not a single age cluster. So we are seeing a population of clusters that are formed, population of stars that are formed over last 50 million years. So that's the kind of population it has. So the total mass of these stars is around 10 to the 5 solar masses formed over these 50 million years. It's a cumulative graph of the mass, which is I should go away from that. My problem is this.
Yeah.
Yeah, if I go.
Yeah.
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 Okay. See, that,
And this one I'm asking.
Yeah.
Inside bubble, you are saying the stars are more bright. Younger.
Yeah.
So I'm saying the outer edge, they are so because of the extinction, they are very faint.
Yeah.
That's why you are saying that in question.
Yeah, I got your point, but here, well, I'm not showing in this all the plots. If you analyze the color magnitude plots of individually for each of these regions, so the stars in this disk stars inside the bubble are somewhat bluer, around estimated something like 0.4 magnitude difference could be there in visual extinction between these two regions. So outside in the disk around 0.4 magnitude extinction, inside it is inside the bubble it's 0 magnitude. So it will not affect the result discussed here. So there can be small differences in this what is that, the height of this plots, or including the age, because it affects the color also. Okay. Well, the next question we addressed is energetics. So now that we know that there are not very young, but there are recently formed stars, and that it's expanding. So then whether the stars inside are able to generate this bubble. So we use the standard hydrodynamical equation for the wind-driven bubbles. So where the radius today at time t is given by this equation, where L mechanical is the mechanical energy output from stars in the form of either stellar winds and supernova explosions, and rho gas is the surrounding uniform gas density, ISM gas density. So here the assumption is that the bubble is formed in a uniform gas, then it expands, collecting more and more mass, and then this mass collected will be M shell. No? That's what we are measuring. So the equation can be also inverted to calculate what mechanical energy is required to explain the observed parameters like mass of the shell, radius of the shell, and the expansion velocity of the shell. So if you substitute the values in this equation, we get that we require something like 2 times 10⁻38 joules per second of energy, which can be very easily obtained from the number of stars that we have detected. So it actually, if all these 10⁵ solar mass stars were created at a single epoch, then there will be 20 times excess energy. But here, what happened is this is distributed over 50 million years, and it is able to maintain that, because I mean, what happens if all the energy is liberated at a single time? Bubbles will be destroyed. So actually, there will be a blowout. It means that the energy bubble will expand and immediately reach the scale height, and the entire energy is wasted into the halo. So it won't be used to expand the bubble. Whereas here, the continuous scenario of formation of stars probably has helped the bubble to grow slowly and steadily to reach this large sizes. So that is the idea which I am again using, and it looks like that is the real idea, or the real process in this in this region. So,
So is it like only the scalar wind is responsible for the formation of?
No, there may be supernova also. Yeah,
But in the mechanical, what you have calculated?
it includes also supernova energy.
So then how you calculate that? You assume the probability of having supernova within a.
Well, this use the results from Starburst 99. So which includes, I mean, in a cluster, we know exactly, given the solar mass, how many stars are there about 8 solar masses. So then I know exactly how many supernova will explode in a given time. So that is completely analytically, you can calculate how much stars are there that can explode. So that's what it is done in this Starburst models. Actually, it's much difficult to include the stellar winds, but supernova is much easier. So I am plotting here the ages of the stars. Now that we have ages for every star, so the youngest ones are less than 10 million years. They are plotted in the yellow. There are very few of them, and the others, which are between 10 and 20, are in the purple circles. So other older stars I have not indicated, but all these other blue ones are older than 20 million years. So you can see that they are distributed everywhere, but there is a tendency for these relatively younger stars to be at the edges of this cavity, closer to the shell. So that is, in fact, as I mentioned earlier, so here you can see this. This is a cluster-like thing, but this radius is 100 parsec. So there is a shell also around that, mini shell, you can say. So, and overall, this is 1 kiloparsec almost. So this is 100 parsecs, I see. So, and also in this plot, I am showing the 21 micron contours in red. So wherever H alpha bright regions are there, exactly coincide with the 21 micron sources. So these sources cannot be older than 4 million years. They're probably younger than 1 million years. So around that age. So youngest stars, if there's a clear evidence that the youngest stars are around in the shell, whereas slightly younger stars are inside that shell, but in the edges. So these stars in the shell are formed by the trigger because they're the youngest. So the previous generation of stars are formed just inside. It is giving an indication that clearly there's an age gradient. So something happened in the middle, and after that, star formation just continued propagating outward, and we see the most recent star formation in this shell right now. So not to illustrate this age gradient, I present this somewhat complicated plot. So where I show the ages of all stars as a function of radial distance from the bubble center. So the old stars, relatively old stars, are distributed in throughout the bubble, so they are there in all radius. But youngest stars are not there in the bubble center, so they are more and more concentrated. This is the line that suggests that there is an age gradient. So they are more and more towards the edges, and at the shell, basically, we have the youngest stars, which I here assigned 4 million years for all these regions, which are called as A, B, C, D.
Can't it be related with the expansion, what you were talking about? If you calculate the time scale of the
Yeah.
expansion, I mean, if you have a continuous, star forming things, it is connected with the boundaries, and the boundary itself is expanding.
Exactly, that's exactly the model I'm proposing. Thank you. So that is the model I'm proposing. So first generation of stars somewhere formed there. So then whenever the first mechanical energy input was there, it started expanding and forming the first shell. Then it got dense enough to form new generation of stars, so which again gave more and more energy, and the process continued. So up to the present age, no? That's the reason we are giving here to explain the distribution of stars everywhere. So it's not clustered. Probably only stars are formed in the distributed way, not clustered. So in this kind of scenarios, no. So usually, I mean, all these star formation scenarios pertain to quiet regions.
Pop kind of thing.
Yeah, where molecular cloud collapses and forms a cluster. No, whereas here it is externally triggered. So then it looks like stars form and continuously it's getting pushed. So location of next generation of stars is now different. It forms that's different radius. So if you see it after 50 million years, that's what we see. So that's exactly the model we are proposing to explain. So this kind of models are new. So we call it star formation in an expanding bubble. So we can, I mean, we will do more numerical work on this to see whether it works. So that's for future. Okay, just to finish. So I think for the discussion, I have convinced you that the stellar energy output from stars over the past 50 million years is responsible for creating this big bubble. So already by other studies over the last 2 decades, we know that other bubbles, smaller bubbles, are created using the same process. And then the question is, why only one of them is so big in this whole image? So we believe that reasons are these two. So in this region, we see that it's not a single cluster. There's a multiple generation of stars over 50 million years. So, and that probably happened because the first generation of stars in this happened in the interarm region. So you can see the spiral arm. So the center is clearly shifted from the 2 arms. So it is somewhere here in the interarm region for some reason. So the star formation started there, probably not at a very high rate. High rate means it will destroy everything around. So so that's why it could trigger this process that I described just a minute ago. No? So it just started having its first shell of expansion, and finally it started forming more stars, and the shell kept on expanding until it reached the boundaries, which in this side boundary is the spiral arm. In the other side also there is the spiral arm, and in fact in this side it is the low density side, right? Wherever spiral arm is there, a higher density, and then density gradient is along this. So it is slightly elliptical, and it's opened also in this side. No? Probably this is as much big it can get. That cannot get much bigger than probably 1 kiloparsec. So that is such events getting stars forming in interarm region are not that common. maybe that is the reason why we don't see such big bubbles generally. So that is the conclusions I have.
But
So-
it has to be triggered by something. I mean,
Triggered by something. That
because, if you just look at the dispersion of the entire, galaxy, it's all arms and so on. And if you put some perturbation somewhere, I mean, numerical things,
Yeah.
we can imagine whether it will, result in some kind of such formation.
There are other papers now came from this this same data. So there are structures that connect spiral arms here. Look, there are structures in this image. You can see structures,
Yeah.
especially these structures, and there are star forming sites in these structures. So looks like you can form stars also in the interarm regions. So they're not that common. Don't know how to create these structures. So such process might have happened here, and so that is the reason for it.
So any galaxy simulation, I do not know what is the most advanced galaxy simulations.
They have passed the scale now.
They have good scale,
Yeah, yeah.
so whether they could generate any of these, I mean, bubbles and all that in the interarm.
Probably have no motivation. The capacity is there, so I think.
Some additional
That-
input is
that's
required.
Is there any illustrative simulation is there for this kind?
uh,
Like they have this simulated all of the galaxies and.
yeah. I have not looked at that illustration, but that's more of interacting galaxies and all they have, not the bubbles.
So maybe I could confuse here. So you said that this bubble is quite large and larger than the other small bubbles.
Yeah.
Is it because it is getting powered by multiple generation of the stars and continue to expand?
Exactly, that's one
So with
reason.
other bubbles, these multiple generation of stars are not present, or what is the?
Yeah, other bubbles, multiple, the first generation stars are usually intense, I mean, usually massive. So since if they are generated in the spiral arm, they will get into a particular size, and if the energy generated much, they will open up in the vertical direction. So then the bubble will not expand more.
Fuel is gone.
Yeah, fuel is gone, and it's all input, all the energy is input at the same time. So here the first generation probably is it's around 10⁴ solar masses only. So that is still able to maintain within the radius of around 200 parsecs, and then the energy is maintained. So that's the idea behind this. One has to do exactly the numerical calculation at good 3D models to exactly confirm my quality. This is qualitative explanation right now. So the idea is that, and usually in the spiral arms, when the clusters form, they are massive. So they destroy the, I mean, they can only reach around 50 parsecs and before they get destructed, or there is another star forming site close by, so that will merge with the expanding bubble also. That also is there. Stellar density is also higher, star formation density. So that will also coalesce, different bubbles.
Is it also the reason I'm just thinking about that if it is in the arm region, so because of the density and ram pressure outside is much larger, so it stops the bubble from expanding, given a particular amount of energy.
Yeah.
In comparison to when it is present in the interarm ring.
That's perfectly all right. Yes, the density is higher. So
Because in your equation of RG, there was rho gas and that was a
Yeah.
surrounding region.
exactly,
If
that's
it is
correct.
larger, then it will, the bubble will be smaller.
Smaller. Yeah, that's I didn't explicitly tell. That's also another reason. Yeah, so I think I will not read these conclusions, but so just general conclusion is that the big bubble is generated by the feedback effects of massive stars. Here, the cluster mass, total cluster mass is only 10⁵ solar mass, which in extragalactic field not very big. Like starburst galaxies like Mayya, which I had studied intensively, many clusters are there of million solar masses. So this is really overall mass of stars formed over 10 to the over 50 million years is very less than the solar mass. No? So that is the condition that has generated this big bubble. Now, so before I finish, I just want to show you some pictures. We are in the mountain region here, so I am also in the mountain region. So this is a view from my office. So this we have. This is a volcano called as Popocatépetl. Somebody can repeat. So it means smoking mountain. In this photo, I didn't get the smoke. Usually it is smoking, so it's active but not destructive. So it is slow and steady kind of mountain. So
It was the last eruption.
a big blast eruption around more than 100 years ago. Yeah, it was quiet. It was quiet until 1990s, 94, I think. 94 onwards. Ever since I was there, always smoke, every day smoke is there. So this is the night vision.
You can go closer. I mean,
We can go, always I miss how to go back. We can go up to this saddle point, this point. Then there is some police guarding here, so that you don't go up. On this mountain you can go. This is 5,600. So this is around 5,100. Here you can go. So usually this this doesn't have snow because it's hot, and only in the winter's few days you get it like that. So this always is snow covered. So
your observatory and all that, why don't you say two words about also the millimeter thing which you are.
yeah, I was talking to Dipankar that we have an observatory which works in millimeter wavelengths. So which is called the telescope is called a large millimeter telescope or LMT. So it's a 50-meter dish. So which has participated in the Event Horizon telescope that gave you now well-known images. No, that orange images. So, so that telescope is at a height of 4,600 meters. It is diametrically opposite. We are in the middle of these two big mountains. Well, that is also a peak. I mean, that's like a peak. Like there's a big mountain. Biggest mountain in Mexico is a little bigger than this, around 5,800. So that is closer to the telescope, but the telescope is at 4,600 meters. So this telescope is Mexican with some collaboration from US. So we have around 70% time on that and 30% JUMAS, University of Massachusetts, along with the US. No? So that has a lot of instruments, spectrographs, and imaging at the millimeter between 1 to 3 micron region. So anybody else is more interested, I'll be happy to share information with you.
Okay, so let's thank Professor Divakara for the Now we have time for question and answer. So feel free to ask any questions or anything, young students. Yes. Yeah, please.
So you have found like over densities in longer wavelength in the population in population.
I didn't get the first.
Over density, like density of the star in the outer regions, young stars.
Outer means in the shell region. Yeah. Actually, we look for over densities only inside the shell, in the cavity. Okay. So in the shell itself, because of the extinction suffered by, because so much molecular gas is there, so there are, optically we don't see anything there. Yeah. So we haven't looked. I mean, there is no over density. Whatever stars are there, they are very young. Rather, they're still within their molecular clouds.
In all of your images, we saw the certain demarcation between the gravity and
Yeah.
So, is it true that actually there was none a young object inside?
Yeah, because I am showing only the JWST NIRI images in all this. JWST NIRI images are sensitive to more ISM than stars. So at more than 5 micron, the stellar radiation is very, very low. So any ISM, any lines or ISM will be one which will be visible. No? So only when I make images using optical and infrared, so I can see the stars together. No? That's what some of the images I had. No? Yeah. This. So here you can give, but if I do the same thing for all the other bubbles, yeah, there are these stars.
Yes, sir, I have. So do we have any information regarding the masses of the stars within that bubble?
Yeah.
What are the typical masses of the stars that are within the bubble?
Yeah, because of this. Let me go.
So that is necessary to understand whether what type of supernova can happen. And
Yeah, exactly. So indirectly, this plot gives you the masses, because this is the isochron for 3 million years. I have the
There was one other plot.
Yeah. I come to that. This, okay, yeah. So this is for 3 million years. So a turn of age for 3 million years is around. Turn of mass for 3 million years is around 100 solar masses. Okay. So there are no stars there. So these stars which are here, they may have something like 50 or 60 solar masses. That depends on, because they have around 5 million years.
even if there are few stars within 20 or above, they can result into, I mean, porous supernova and trigger the radius of the bubble can increase.
Yeah, that's what we are. This is what is today, no? So, but there were stars also here, but since they're old, they're already old. So, whatever has gone into the expansion, we are not seeing it. Okay? That's the assumption when we use.
Any information regarding the number? How many of them would have gone?
Yeah, this required something like 400 supernova
That
explosions.
is based on the energy index.
Yeah, mass for a 10⁵ solar mass cluster. Generally would have around 400 solar masses. I mean, 400 supernova events.
Yeah, I think it's interesting. Supernova occurrence density. Some of the more similar galaxies can correlate with this evolution of stars. Powering by supernova.
Yeah. Yeah, it would be good really to look, detect the supernova. No? Here is based on the energetics we estimate. So we haven't looked for radio data to see there are remnants. So these things are remaining. We need at a similar resolution to detect them. No? So if they are compact remnants, so this will be
400 supernova from only that much. That reason is really
big number. Yeah.
it is, like in
Core collapse supernova. Yeah. Exactly.
Little outside from the topic. Can you say something about the JWST data release, like what type of products are
Yeah.
there?
Yeah, thanks for asking this question, because JWST data can be accessed through MAST. You have known what is MAST. So the MAST portal, you can download that like any other data from NASA products. No, so the way to access that is if you know the object name, whatever your favorite object name you give. If JWST box comes, it means it has been observed, or it has been proposed by the JWST, whoever observed. So once you go there, you will get all the information about why people have asked for the such and such data and which filters it has been observed, or it will be observed in future. So all the information is there. So the data release is completely the reduced data, completely processed data. So it is astrometrically calibrated. There is all information for the photometric calibration also. So you can like we did directly, if you know other things, you can directly use these data. And policy, there is something called that you mentioned early science release. Data is the immediate. The day they observe, whenever within 2 days, they will put it to all people. Although these observations are basically planned by the instrumentation group or by the JWST group itself. So, but it's available for any other people to download. So, in this case, my data, all I forgot to mention that written there. It's all part of FANGS project. FANGS is a survey of nearby galaxies. JWST will observe 19 of these galaxies. Already 11 galaxies have been observed. So this is the first galaxy. So these data are public immediately because it is observed in that condition. So many data are already public. Yeah, whatever is observed, it is public. So this has spectroscopy, which covers big range. It has NIRspec that covers the near infrared range, and MRS is called the 5 to 30 micron range. So with decent resolutions, some around 2000 ISO resolutions. 2000, sorry. So we can do. It's all new science. We haven't worked. Many people haven't worked with what chemical lines. What you get from these frequencies, So actually, in 2 days' time is the deadline for the next call. First call actually after the release of the data.
Yeah, so if there are no further questions, then let's thank again the speaker. And
Thank you.
One important announcement to make for the faculty who are taking the class of the first year students. This facility is again resumed with the touch panel guides and all those things. These are advanced and highly tuned systems to kindly shift all classes from council room to auditorium tomorrow online. If you feel any problem in it, kindly let us know. So, is there any dedicated module for that? सर ये पैनल पूरा आपको एक्सेस मिलेगा इसका यूनिटी वगैरह सब इसी पे मिलेगा सर तो ये टच पैनल के साथ है अब आपको डेडिकेटली पूरा स्क्रीन आपको एक्सेस मिल जाएगा वो वायरलेस कीबोर्ड माउस के साथ अपडेट है डायरेक्टली पेन ड्राइव से यहाँ से लगाइए फिर हैव द एक्सेस
It's all right. This question. Divakara is here until day after tomorrow morning. He will be to Bombay. So he's sitting in the email in the ground floor. NGC. Anyway, he'll be around outside the center. Yeah, we can meet here also. Yeah,